Good morning. My name is Steve Minnie, and I'm the Senior Director of Applications in the AFM Business Unit at Bruker. And I'd like to welcome you to this installment of the Bruker AFM webinar series. This presentation is titled Mapping Graphene Surface Potential with Less than 20 nanometers Resolution, and it's presented by Greg Andreev and Aravind Vijayaraghavan. Before I introduce Greg and Aravind, I'd like to make a few quick logistical comments. First, we encourage your participation during the webinar, and if you have a question, please type it into the questions dialog box on your screen. We'll accumulate these questions through the presentation, group them together, and answer them at the end of the prepared remarks. Quite often we have more questions than we can answer in the session, and in those cases we'll be sure to follow up with answers via email. Also, if you'd like to review the presentation afterwards or pass it on to a colleague, the webinar will be posted online shortly after the webinar has concluded. Additionally, you'll receive email with the link to this posting after the webinar is complete. Finally, when you exit the webinar, you'll be asked to take a brief survey, and I'd very much appreciate it if you take the time to complete this, because it helps us pick the topics that are most important to you and generally make this webinar series better. So let's get started, and let me introduce our first presenter, Dr. Greg Andreev. Greg is an applications development scientist and the technical lead for near-field optics in the AFM unit of Bruker's Nano Surface System. He received his PhD from the University of California at San Diego, where he was the first to demonstrate nanoscale imaging of plasmons and graphene. Prior to joining Bruker, Greg was an NSF Fellow at the University of Colorado at Boulder. Dr. Andreev has co-authored over a dozen peer-reviewed publications and is the primary inventor of several patent-pending technologies in near-field optics. Our co-presenter today is Dr. Aravind Vijayaraghavan. Aravind is a lecturer in nanomaterials in the National Graphene Institute at the University of Manchester. His research is focused on graphene electronic devices and sensors. Aravind obtained his PhD from Rensselaer Polytechnic Institute in the USA and has held postdoctoral positions as the Alexander von Humboldt Fellow at the Karlsruhe Institute of Technology and at Massachusetts Institute of Technology. Aravind has 38 papers in international peer-reviewed journals. So now, let me turn it over to Greg and Aravind for their talk titled Mapping Graphene Surface Potential with Less than 20 nanometers Resolution.
All right, thanks, Steve. This is Greg, and let's get started. I will begin with a quick outline of the presentation. We will first have an introduction to graphene by Aravind, and then after that I will go into how PeakForce KPFM works, and then I'll show our results in both air and the GloveBox environment, and afterwards we'll open it up for questions. Okay, let me hand it off to Aravind. Okay.
Yep. Hi, I think that's working now. Just get the presentation up and running. Is that okay now? Can you see it clearly? Yeah, hi. Okay, hi, my name is Aravind. I'm just going to give you a brief introduction to graphene, about just a few things about what graphene is, how we make it, and just a couple of slides about why the PeakForce KPFM mapping of surface potential is important. It's important for various reasons, but I'll give you one or two important reasons why we would like to do that. So some of you might already be well aware about what graphene is, but just as a quick introduction, we have graphene, which is the first two-dimensional material. We have a number of two-dimensional materials these days. Graphene is only the first of many. But it forms the building block for a variety of other nanocarbon systems. You have zero-dimensional buckyballs, one-dimensional nanotubes, and 3D graphite, of course. And you can roll or stack the graphene up in different ways to get these structures. And how we make graphene, like for example, the samples that Greg will be talking about today, they were made using what we call the Micromechanical cleavage method, or more colloquially the Scotch tape or sellotape method. As the cartoon shows, you put down a piece of sellotape on a piece of graphite, peel off a few layers on the sellotape and then transfer those layers down onto your choice of substrate. It can be silicon dioxide, it can be silicon nitride, it can be boron nitride. There are a variety of different substrates on which you can put graphene. And then we peel away the tape, which means that you're left with a few layers of graphene on the surface, and then some of these flakes are thick, some of the flakes are thin, and you hunt around and you find the single layer graphene flake. But that's not a scalable method. If you want to use graphene for something, you actually resort to something known as chemical vapor deposition, where you take a metal surface and grow graphene on it as a monolayer using a gas phase carbon source like methane. And then you use a polymer transfer method for transferring the graphene from the metal substrate onto silicon dioxide, nitride, etc., just like we did in the previous case. And I think the big development in graphene, which really sparked the revolution of graphene research, is the finding of the graphene using optical contrast. So as you can see from this graph, if you have a correct matching of the substrate and the optical light that's shining on the graphene, you can get very good contrast even in an optical microscope, and you can easily see the graphene. You don't need an electron microscope or anything like that to see the graphene, which I think is allows you to easily identify, especially like, for example, in the AFM, you can just see the graphene in the optical microscope and go with the tip and look for it there, so which makes life very easy. And also for device fabrication, it makes life very easy. I'll just switch now to, of course, you know, graphene has many amazing properties, but what's very relevant for today's webinar is the electronic properties of graphene. As you might know, graphene can be monolayer, bilayer, trilayer, etc. If we focus on monolayer graphene, you see the electronic density of states, the electronic structure. It has it's a linear density of states, which means that it behaves as direct fermions, and the electrons travel very fast, nearly at the speed of light, and they are massless, so they don't get scattered very easily, etc. And they have extremely high mobility, and they have, or ideally, in the ideal case, they have extremely high mobility, and that's where the substrate and other things come into play. The other thing you'll notice is there are two cones. One is the electrons, one is the holes, and they actually touch each other at a point. So technically speaking, at that point, the number of electrons should be equal to the number of holes, which means you don't have a net charge. But in fact, that's not quite what happens. Depending on the environment in which the graphene is sitting, you might have, or the substrate or the environment, you will see that the resistance of graphene as a function of the number of charge carriers varies quite differently. As I said before, at the direct point, which is the balance between electrons and holes, when you have equal number of electrons and holes, you should have zero net carriers, which means you should have infinite resistance or zero conductivity, but that's not quite what you observe. And the reason for this will become clear later on during the talk when we talk about things like electron hole puddles. But that's when imaging these electron hole puddles become very important. The other reason why we would want to study graphene, charge transfer in graphene, is things like doping, which means if you put any gases or other materials down on graphene, there's usually a charge transfer between the graphene and between the foreign material and the graphene, which basically means that the resistance of graphene depends dramatically on its sensitivity to the environment. In this case, for example, you can use graphene as a gas sensor, which is the advantage, but the disadvantage is that if you put foreign materials down on graphene, then its conductivity, its resistance will change, and this is again as a result of charge transfer. So a visual way of mapping and imaging these charge transfer domains also becomes very important. So that's basically a brief introduction to graphene. I think I can hand over now to Greg to show you the actual results on the KPFM.
All right, thanks, Aravind. All right, So yeah, thank you, Aravind, for that introduction. And now I will introduce KPFM. But before getting into that, let me just briefly mention the importance of lift mode. That is an essential part of KPFM. And what lift mode is basically a way to retrace the surface without actually being in contact with it. So your first trace is your typical AFM trace. You will use tapping mode or, for instance, PeakForce tapping, which is what we prefer. And then your second trace takes the information obtained on the first trace about the surface and simply retraces that exact surface topography, but at a small height above the surface. So the purpose of this is to separate topography from the electric or magnetic information if you're doing MFM. And it helps you with getting rid of artifacts, which is something that I'll touch on later. Okay, so let's talk about KPFM and how it works. So KPFM, the basic principle is that, as you can see from this diagram here, if you have two materials that have different work functions, and then you bring them together and basically create a circuit, then you will have some potential difference that naturally occurs between the surfaces. So this is called the contact potential difference, the VCPD for short. And one way that you can figure out what this difference is by adding a potential to one of the materials until there is no longer any flow of current, and then you can basically cancel out that difference. So by canceling out the voltage difference that's there, you can figure out the work function of the unknown material by using some known material. And so the way that we do that with KPFM is by using a tip, which we know the work function of, to probe materials that we don't know the work function of, and we basically measure this contact potential difference through these equations. And I won't get into too many details, but basically the gist of it is that we try to minimize the force gradient. And the force is described by this equation where the voltage term appears. And as you can see, the VCPD that I mentioned just now appears in this equation. And by oscillating an AC voltage and applying a DC voltage, we can figure out through the mechanical feedback of the tip when we've set the DC voltage to the correct value to cancel out this contact potential difference. So by using the minimization of the force gradient, KPFM allows us to measure the work function difference between the tip and sample. And therefore, if you know the work function of the tip, you can get the work function of the sample. And there are many ways of doing KPFM. The one that I will focus on in this talk is basically using frequency modulation. And let me go into that a little bit. So as I mentioned just now, there are several ways of doing KPFM. And basically, they're composed of two different ways of performing the mechanical feedback, tapping mode or peak force tapping, and two different ways of doing the potential measurement while you're in lift mode. And basically, these are two different ways of performing lock-in detection. And without going into too much detail, basically the FM method is more sensitive, and when combined with peak force tapping is particularly attractive because peak force tapping allows us to use a better suited tip for this application than tapping mode. So KPFM sensitivity is proportional to the, Q over K, and where K is the spring constant and Q is like your quality factor. So the problem with tapping mode is that it kind of works against you for your KPFM sensitivity. And so you would prefer to use a tip that optimizes this ratio, and you can't really do that very easily with tapping mode. So the scaling is in conflict. However, if we use PeakForce tapping, we can use pretty much any tip we want, and we can optimize this simple relationship to optimize the KPFM sensitivity. And in addition, we have access to all the great features of PeakForce tapping, like we can get all these additional channels, such as adhesion or modulus, which give us additional information about the mechanical properties of the sample. Okay, so with that said, I will now go into KPFM measurements performed previously on graphene by some researchers. So this is basically some work that we tried to replicate in a way. And this was published by you and others in Nanoletters in 2009. And in this paper, what they did is they started out with a single aura bilayer sample of graphene, and they used a gold tip to measure the work function using KPFM. And their reasoning was basically as follows. It's summarized in this diagram. By measuring the work function difference between the tip and sample, they argue that they're measuring this energy difference right here that I'm pointing to. And by tuning the gate voltage, they can move this Fermi level through graphene's band diagram, and they can find the minimum position from independent measurements. So they use a gate voltage, and they can figure out what gate voltage corresponds to the Dirac point right here in the middle. And then they can use, they can set the sample to that gate voltage, measure their contact potential difference, and figure out the work function of intrinsic graphene. And the value that they get is approximately 4.6. And this is one of the first papers I found on this technique. And what's interesting about this paper is they also performed these measurements in a nitrogen environment. And the two traces that were in that environment are the blue and black traces here. And as you can see, at a 0 applied gate voltage, they're actually pretty close to intrinsic graphene. You can see that the black and blue are very close to 4.6. And although they don't really stress that in the paper, I think that's very interesting. I think what it suggests is that by simply putting graphene in a controlled environment, you get very close to the intrinsic state of graphene. Okay, so with that said, let's go into our measurements. Well, first let me briefly point out how our measurements are different from this work. The only real difference is that our tip is not made of gold. It's different than the electrode. So in their measurements, they basically argue that their tip is the same as the electrode. And we do not have that situation, so our measurement is a little bit more complicated. So we have to have a slightly different energy diagram. But everything else is basically the same. So let me, oh, and these are the approximate values for all of these quantities that I'm showing here. So let me go into the sample that we studied. So on the right, you will see an optical image of the sample. And we focused on a very small region in the sample where I found some very interesting features that were small enough to test the resolution of our technique. So for instance, there's this scratch through the graphene, and also there is this very thin rod of some sort that is either underneath or on top of the graphene. It's hard to tell. And over here is the silicon nitride window substrate. So why did we use this sample? Well, one of the reasons is that the substrate is largely insulating. It's a silicon nitride window with nothing underneath it. It's just air underneath. So the idea was that KPFM would then probe mostly graphene. There would be very little crosstalk with graphene and, let's say, some other material underneath it, which might be the case in another sample. And I also thought that the roughness of this substrate, although it's not ideal for some other measurements, it might actually be kind of interesting because it would add some sort of structure to graphene. And in the past, people have speculated that it's actually surface variations, topographical variations that allow graphene to exist in the first place. So I wondered how such an extreme case of substrate roughness would influence graphene's properties. Maybe we would see something different that other people did not see. So let me show you the first set of data here. So on the right, I'm showing the potential, the KPFM potential, and I apologize about these labels. They were supposed to pop up a little bit later, but basically on the left you see the AFM image that I showed already on the slide before. But on the right is the KPFM image. This is done in air, and you can immediately see that there's an incredible contrast between the silicon nitride substrate, which we don't expect to even have a force gradient. It should be an insulator, should basically have around 0, but it may have some trapped charges, it may have some contamination. So at the end of the day, it's actually, it does have a slight contact potential difference with the tip, but it's less than 100 millivolts. Graphene, on the other hand, definitely lights up, and you have a very large contrast. And the average, if you take an average of this, of all of the graphene here, you get approximately 0.4, like 3.5 to 0.4 EV, and our tip is around 4.5. So this means that the work function of graphene is approximately 4.85. So we are far away from intrinsic graphene here, because intrinsic graphene should be around 4.6. But another question is, what about all these nanoscale structures that we can also see? Are these real? And well, one immediate argument that I can present that they are real is, for instance, if you look at this linear debris that's indicated by the red arrows, it doesn't really appear in the KPFM image. However, the division between graphene, which you can barely see in the topography, which is this 40 nanometer gap that I'm trying to point to with these blue arrows, that is clearly visible in the KPFM image. So that's actually indicative of a artifact-free measurement. So, but we can do better than that. We can be more convincing. So, for instance, in previous KPFM studies, what we did to rule out topographical artifacts is we varied the lift height. And this is a great example of that. What we did is change the lift height at very small increments until we basically saw this feature inside of this polymer structure suddenly disappear. So this is a pretty solid argument for topographic feedback influencing the KPFM signal. Most likely the tip was still sticking to the surface for these lift heights. And once we got to this lift height, we saw the actual potential of the polymer. So we can do the same thing with graphene. And by the way, if you'd like to learn more about this, it's in our app note number 140. So we did the same thing with graphene. We looked at an area near the, basically an area centered on the cross that I showed you in the previous image. And we varied the lift height from 28 nanometers to 75 nanometers. And the take-home message here is that we did not lose any of these features. They just got a little bit more blurry. So that means these features are not simply due to the tip sticking to the surface, because by the time you're at 75 nanometers, the tapping amplitude I was using was way too small for the tip to be touching here. So because there's no sudden loss of resolution, the contrast is not due to some sort of topographical artifact. So let's, with that said, since we know these KPFM features are, we're very confident that they are real, let's zoom in on an interesting region, for instance, the one that I'm indicating by this black box here. It has this interesting line and some other features that we might see a little bit better. So here's the height image. This is a very small image. It's 750 by 750 nanometers. And you see that there are some sort of structures that we can resolve a little bit in this image. And in the adhesion channel, we see these structures a little bit better. And because essentially we got rid of the topography and we only have structures that have a different force response. So with these two channels combined, we can get a lot of information about the mechanical properties. And it seems to suggest that there's some sort of residue underneath the graphene. And maybe this is some sort of photoresist left over from when the contacts are made on these samples. So the question is, will this contamination or leftover photoresist have any effect on graphene's work function? And what about this topography? As I was asking earlier, what effect would topography have on graphene's work function? Okay, well, let's take a look at the corresponding KPFM image. So here it is. And we see right away that it exhibits a pretty large amount of variation. Actually, if you look at this profile here, it briefly goes through a dark region over here, which drops on the order of 100 millivolts down from these brighter regions. And also over here, the region that I'm indicating by this dark red arrow is shown here, and this region is only 20 nanometers wide. So it's pretty impressive that we can resolve this with KPFM. It's a very powerful example of the kind of resolution that you can get. And in addition to spatial resolution, we have really nice energy resolution. So we have the work function resolution necessary to resolve these materials. If we did not have resolution on the order of 10 millivolts, then it would be very difficult to tell these regions apart, which differ sometimes only by about 50 millivolts or less. So clearly there is a great deal of inhomogeneity revealed by KPFM on this sample. And it actually looks pretty similar to what Martin and others saw in a very famous paper in Nature in 2007, where, of course, these measurements were performed in vacuum, but nevertheless, and their sample was extremely clean, but nevertheless, they saw some variations that were about a third of what I'm seeing here. And they attributed these variations to the substrate, some sort of charges in the substrate. So we may have a different origin for these sorts of puddles. It may be some combination of factors, but The length scales are very similar. For instance, the length scales here are about 300 nanometers to 500 nanometers. Our length scales are 300 nanometers on the order of that, sometimes as low as 50 nanometers. So let's see if there's any correlation between this KPFM image and our topography images, which I showed earlier, and the adhesion image. So here's the adhesion image on the left, and here's just the higher portion of the KPFM image overlaid. It's pretty clear that the KPFM image is preferentially higher in the regions that seem to have a larger concentration of these of this residue, these little specks of perhaps photoresist. I'm not sure exactly what it is, but it's some sort of residue. It's not just roughness in the substrate. And interestingly enough, it seems to increase the work function of graphene. So as far as instrumentation goes, this definitely demonstrates that having this additional channel is key to doing a correlation like this. It's very nice to just completely flatten the image, essentially, by looking at the adhesion channel, and you can just immediately tell where your different materials are. So this also raises an interesting question. What is the doping mechanism for these regions? Is it related to water and oxygen, as was thought previously by other researchers? Because if this is some sort of residue, maybe this is a different type of doping mechanism. So in order to answer such a question, we have to have some sort of environmental control. And the general question of what effect the environment plays on graphene doping, you might want to know what role water plays, oxygen, and is this reversible? So what you need is a way to do KPFM in an environmental controlled environment. And of course, you could have a cryogenic UHV chamber, but that's costly and sort of difficult to use. It would be great if there was an alternative, which was a lot more convenient to use. And we have an alternative which can get you results that are very close to what you would achieve in such an environment. And the alternative that we can offer is the GloveBox Integrated System, which I'm showing here. It has a argon atmosphere, and this basically gets rid of the water and oxygen that could dope your graphene sample and create some kind of contamination. And we can reduce the concentrations of water and oxygen to below 1 part per million. And you can also pump your sample down by putting it into an antechamber, and there's a turbo pump connected to it, which allows you to evacuate your chamber for some period of time. So that's what we did with this exact same sample, and we used the same tip, and we evacuated the sample and then performed KPFM in the same region. And just really quickly, the physical picture for what we might expect to happen is shown here. So in an ambient environment, graphene is hole doped by water and oxygen and perhaps some contaminants between graphene and the substrate. In the glove box, the water and oxygen are removed. So you're removing a portion of the dopants that were creating the hole doping. So you should expect the Fermi energy to go towards the Dirac point, go towards 0, and you should expect the measured work function to decrease. So if water and oxygen dominate, then potentially by simply using a GloveBox, you have a method for studying nearly intrinsic graphene without any cryogenics or UG. So let me show you some results. So on the left, you see the ambient data, and on the right, you see data in a GloveBox of the same exact region and then the same tip. However, it's a different scale. But what is clear from this image is that the contrast between graphene and silicon nitride is greatly reduced. And the spatial inhomogeneities in graphene are also reduced. And I'll demonstrate that in a couple of slides. But we can also try to put this image on the same scale. And if you put it on the same scale, it's basically, well, it just kind of looks like an insulator. And the graphene signal is much lower. Now, there's a caveat to this claim. It's not a 100% accurate statement, because if you have an insulator, it's difficult to do KPFM on it. So, because what's going to create the response in your material to give you a force gradient that you're going to measure. So the closer you get to an insulator, the less reliable your measurements will become. So you have to sort of take the absolute values here with a grain of salt. However, it does make intuitive sense that if graphene is very much responding like an insulator, as we know this material is an insulator, and graphene is responding in a very similar fashion, then it's a pretty solid argument that we've reduced its work function. So we can actually quantify that, and the numbers that I get are that the graphene's work function was reduced to very close to 4.6, which is very close to intrinsic graphene. And let's look at the same region that I showed you earlier. The same region that I zoomed in on earlier, this was in air, is shown here on the right. When we perform the same measurement, KPFM measurement in the GloveBox, and we put it on the same scale, we see that the contrast inside of graphene is greatly reduced. And as you can see, the AFM doesn't change too much. It got a little bit blurrier because I think the tip was starting to wear out. But basically, the contrast is gone, and it's not. It seems to have rearranged itself a little bit too. So this is another argument that graphene has changed in a significant way, and it has become more homogeneous, and it has become less conducting. So to make sure that this effect is real, we also performed this measurement on another sample on the same substrate. It's just a different area, and so it's the same silicon nitride, the same electrode. It's just a different part of the sample. And when we scanned a larger area, we saw an image like this in KPFM in air. And if we do look at a histogram analysis of the gold and graphene region, we see that there's approximately on the order of 100 millivolts difference between graphene and this gold electrode. And the gold electrode doesn't quite have the work function of gold that you might look up in literature. It's a little bit lower, and that's because it's not purely gold. There's some sort of layer on top of it and maybe a little bit of contamination. So its work function is actually on the order of 4.9. So that means that graphene on this part of the sample is 4.8 or so, which is basically the same as what we saw on the previous sample. But I do want to point out something interesting. If you look up here, This is still single-layer graphene. This is not some sort of bilayer. This is not like a tri-layer. This is all one piece of graphene, but for some reason, you have these steps in potential, which decrease the work function of graphene rather rapidly. It's actually lowered by something like 200 millivolts. And it's not entirely clear to me why this would happen. One hypothesis is that it could be that graphene is lifting off a little bit. Maybe there's a gap between graphene and the substrate here. Maybe it's not firmly connected. So maybe it's acting as more of an insulator here because it's losing some of the dopants that were coming from the substrate, or maybe the trapped water layer between graphene and the substrate. So that was just something kind of interesting that we don't have a very clear explanation for, but nevertheless it's intriguing. So what happens to this same region if we put it in a glove box? So here are two sets of images. The top one, we actually did an experiment in two phases. We first put the sample into the glove box without evacuating the sample, and we just measured it as is. And we got this result. We got about 130 millivolts difference between graphene and gold. And then we put it in the glove box after evacuating it, and we got an even lower work function for graphene. So this is a more convincing proof that relative to gold, you are reducing the work function. And we know gold is around 4.9 in this situation. So graphene must be around 4.7 or so near this gold contact, and may even be lower in these regions over here. And at the very least, this proves that the glove box environment reduced the graphene work function by at least 100 millivolts. So let me conclude the presentation. We have demonstrated that the PeakForce KPFM's spatial resolution is great. You can get 20 nanometer resolved images on graphene. We also show that it's pretty sensitive. We have 10 milli electron volt sensitivity that allowed us to easily distinguish the inhomogeneities in graphene. And we also showed that the GloveBox Integrated System is a convenient, promising environment for potentially studying intrinsic graphene or nearly intrinsic graphene. Of course, there's a lot of work to be done to figure out exactly under what conditions you can achieve that, but it does seem like it certainly takes you in that direction. And with that, I would like to conclude and open things up for questions.
All right, great. Thank you very much, Greg and Aravind. We have a lot of questions that have come in. If you have additional questions, please type them in, and we'll see if we can get to them. So I'll try to group the questions together so we can answer as many as we can. I think that they're coming in sort of three main categories. The first category is sort of motivation for the entire experiment. The second is details of the experiment. That's definitely by far the largest. And then the third is sort of variations or things that you could do for the next step. So I guess to start with the first in terms of motivation, and perhaps either Aravind or Greg, please jump in and answer, but maybe this is for Aravind, which is sort of a series of questions on the motivation of how does one dope graphene, or why does one want to dope graphene, and is that of commercial importance?
Well, yeah, I mean, you want to study doping interactions of graphene with other gases and substrates from a sensor perspective. For example, if you want to try and do something useful with it, or from an electronics perspective, you want to try and minimize or control the doping. You might want doping for certain semiconductor if you're trying to make a PN junction or something like that, or you might not want doping depending on what you're trying to do. And when you have doping, you are always asking the question, is the doping uniform or non-uniform? You ideally want uniform doping. You don't want non-uniform doping. So yeah, so to study the level and the distribution of doping is very important.
So is the doping conducted by, sort of as described in this experiment, by putting things on top of or underneath the graphene, or is it by actually changing the graphene structure itself?
Well, the doping we're talking about here is by absorbing either, you can dope it chemically by gas or solid absorption. You can attach molecules to it, or you can dope it electronically by applying a bias to the graphene, or you can, well, we're not really talking about substitutional doping where we're actually putting other atoms like nitrogen doped graphene. We're not quite talking about that here. We're only talking about charge transfer doping by things that are in contact with the graphene.
Okay. And then sort of along the same lines, why does graphene become an insulator if the dopants are removed?
If you have absolutely no doping, then graphene is not an insulator. It's only, theoretically, if you have equal numbers of electrons and holes, then you're at what is known as the Dirac point. At that point, you have equal number of electrons and holes which have equal mobility. Therefore, the net conductivity of graphene becomes 0. But that is a very, 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 it's only at a certain single point, and you can only really achieve that point at 0 Kelvin when you don't have any thermally activated carriers. But what happens when you have doping, or when you have inhomogeneity, like islands of electrons and holes, is that when you try to reach the Dirac point, you don't get 0 conductivity. You actually get fairly high conductivity because the electrons and holes don't cancel each other out.
Okay. So this may be starting to move into the actual experiment, but along the same lines. What is the doping that you think you're removing? Is it ambient doping or physisorbed gaseous species? And then sort of along the same lines, a couple questions on that. Are removing moisture or oxygen?
Well, I can answer yeah, I think Aravind, you might better answer the first question. But the second question is that the GloveBox removes both. You basically have a controlled argon atmosphere that always has less than approximately less than 1 part per million H2O and O2. And just really quick, I do want to kind of chime in on the previous question too. Yeah, it's just insulator-like. I was referring to graphene as being insulator-like in terms of the signals that you get almost appear as if they are coming from an insulator, but Aravind is of course correct. It's still a pretty decent conductor, even though you've basically brought it near the Dirac point. And yeah, Aravind, maybe you can answer this question about what exactly the dopants do.
Well, I mean, the dopants, if you're talking about oxygen, it's a P dopant. So effectively, when you have oxygen absorbed, the absorption process results in charge transfer between the or interaction between the orbitals of graphene and oxygen, and then you have P doping. But in this case, if you're talking about photoresist or something like that, again, it's also an organic material, and there's going to be charge transfer interaction between the graphene and the resist. Effectively, what you're doing is you're changing the number of charge carriers, electrons or holes in the graphene by absorbing either polymers or oxygen or moisture. Usually, if even if graphene is perfectly clean, you still get a huge amount of doping from the water, from the moisture and the oxygen that's dissolved in the moisture that's absorbed onto the graphene, and you also get a huge amount of doping from the substrate that's underneath the graphene as well. And this is charge transfer interactions.
Okay, so sort of continuing to move into the experiments a little bit more, maybe decent transition is there's a couple questions on the preparation and if you used heating, or should you, or would it be interesting to use heating or any sort of annealing to further remove
water or absorb it?
Yeah, that's an excellent question. We did not use any heating, but that is something that we would like to try and see how much difference it makes. But basically, the sample was just measured as prepared.
Okay. And then also about the setup, these questions came more so at the start of the presentation, but a number on how are you estimating the work function of your tip, or what did you use to quantify the work function of your tip? I think you said it was 4.5, and there's some questions on where that came from.
Okay, that's a good question. So the 4.5 comes from measuring some calibration samples, and we can measure 2 different materials, and we can tell the difference between them, and we can use that to quantify the tip's work function. But also these tips are fairly reproducible. They tend to cluster around 4.5, and for this experiment, I measured the work function of the tip relative to a gold electrode, but that does have the caveat that the gold electrode doesn't necessarily have the work function you'd find in literature. So I went with the work function that was given in the paper of U et al. From the Nanoletters paper in 2009. And basically in that paper they had values that were from, they were in the 4.9, 4.8 range. So there are some error bars that are, of course, around all of these numbers. They're around 100 millivolts. So the absolute values are difficult to know exactly, but they're in that range.
Okay, and what tip did you specifically use?
Yeah, the tip is called the PFQNE -AL. The -AL is for aluminum.
Okay. And then also a number of questions. These were also a little bit more at the start on resolution and how you're determining the ultimate resolution that you get with the different techniques. I think that was before some of the slides that you put up. Those questions were asked, but perhaps you can just review your resolution, or what's driving your resolution claims.
Well, I'm guessing the questions are referring to the claim for 20 nanometers. That's my guess. So let me bring up that slide. So the claim for the 20 nanometer resolution, I mean, if the person is still there that asked that question, they could try and clarify it if they're still on the line.
Yeah, so I guess specifically, probably one example is you say that you have incredible contrast. How does this compare to basic KPFM compared to the PF KPFM?
Well, that's a good question. I did not do that comparison. I did not perform an exhaustive study using every single type of KPFM. I guess I was primarily interested in demonstrating what you could do with PeakForce KPFM because I wanted the adhesion channel and I wanted the guarantee that I would be able to use small lift heights, and I wanted the guarantee that I could use this specific tip. With another tip, might be able to reproduce this result, I might not, but with this method, every single tip I tried, I got a good result. So I didn't have to do any guesswork, really. So I guess it was more like a question of time and convenience, if you want to put it that way. But the resolution, I feel like, is demonstrated. Maybe you can question the exact number. Maybe it's not 20. Maybe you could argue it's 30. But I feel like it's pretty clear that if there is a feature there around 20 nanometers, you can resolve it. You can make it out. So that's why I went with the 20 nanometer number. I saw edges that were sharper than 20 nanometers, and I saw features that were as small as 20 nanometers.
Okay. So we actually have quite a few other questions, fairly detailed on the setup. But in our last 5 minutes, to sort of make sure we get some from each of the 3 categories, I'm going to switch over to maybe questions that are about next steps. And so a question here is, did you try manipulating the charge puddles around by pressing down with the tip? Joe Lighting recently reported similar STM images where the inhomogeneities were attributed to trapped water, and it doesn't go on, but ostensibly was able to affect them with force.
No, we did not try to manipulate them. That's a pretty interesting idea. The problem is if you apply too much force, the lift mode becomes, well, in my experience, it's not as good because you may actually either bend the cantilever or you may actually start to deform the surface. And you really need to use as low of a force as possible to get these kinds of results. So these results were obtained using 800 piconewtons. It's difficult to do with tapping mode. With PeakForce tapping, it's pretty routine. I just type in the number and there's no problem. So yeah, it would be great to manipulate the puddles, but I don't know if force is the way to do it. You may have a very limited amount of things you can do, but you may start to deteriorate your image quality and you might lose the resolution that you need to see these puddles, unfortunately. If there's another way to manipulate them, perhaps electronically somehow, or with temperature, or I'm not sure. But if there's another way to do it, that would be interesting. And if you have some ideas, then perhaps you should send us an email and we can try them.
Yeah, that's a good segue into another question, sort of asking a similar thing about applying a gate bias or being able to electrostatically dope the graphene. Is that possible or something we have planned?
Yeah, we actually really wanted to do that on these samples, but we did not get around to it just due to time constraints. But that is on our list of things to do, and we may, we may do another webinar in the future on that.
And then maybe this is for Aravind. Is there a cap that can be put over the graphene to protect it from this contamination, but would also allow these work function measurements?
You can consider putting a very, very thin layer of boron nitride or something. People have made sandwiches of graphene between 2 sheets of boron nitride. Very often you can eliminate the contamination by annealing as well, which we have done too, so that there are ways to eliminate or minimize the contamination. There are other issues that creep in if you try to put boron nitride. You can put other dielectrics, you can evaporate or sputter other dielectrics, but encapsulation of the graphene is actually a very interesting and active area of research. People are looking into various options, but on the other hand, if you put too thick of an encapsulation, or maybe an insulator will not screen the charges, but if you put a perfect insulator won't screen the charges. But yeah, I don't know how thick of an insulator you can put on there before you can actually still measure the underlying graphene. I guess the lift mode is an answer for that, because the height of the lift mode, if you're still seeing the charge puddles, which means if you have an insulator of that thickness, you'll still be able to see it. But yeah, there are ways of doing that.
Okay. And then this is sort of a half clarification, half next step. They're asking if it's correct that the graphene was measured on a suspended nitride membrane, and then do we have plans to measure just a suspended monolayer of graphene? So I guess asking without the nitride support.
Oh, yeah, that would be great. That would be a very interesting measurement. These sorts of samples are sort of hard to come by, but yeah, I would love to try a suspended graphene measurement. You may run into some problems because these samples are usually very small, and you will be close to the electrode. So you may have an issue with the electrode locally influencing the work function that you measure, which I sort of saw a hint of on my huge scan that I did, where I saw graphene being different near the gold electrode, and then having a lower work function farther away. So yeah, it would not be an easy experiment, but it would be very interesting. And I think the first part of your question was verifying that it's indeed a suspended window of silicon nitride, and yes, it's a silicon nitride window with nothing below it, basically.
Okay. And with that, we're a little bit over time, and so I guess there's one last question. If this webinar is archived, and yes, it is, you will be receiving a link when a link shortly after this webinar concludes. Once it's posted, about where to get that. Right after the webinar ends, you'll be asked to take a survey, which we would appreciate that if you could do that. And so let me once again thank our two presenters, Dr. Aravind Vijayaraghavan and Dr. Greg Andreev, for the excellent presentation today. Thanks again, guys, and bye, everybody.